Hi everyone. In this short video, I'll be discussing the concept of power grid resilience, what it is, how it is modeled, how it should be modeled, and what challenges and opportunities utilities face when addressing resilience. There are a lot of factors that threaten the reliability and security of the modern power grid. First and foremost, the grid consists of many assets that have either reached the end of their useful life or have already surpassed it. This, coupled with all the operational stresses due to either growing demand or the new types of demand, such as electric transportation, means that assets are more prone to failures. Plus, for a lot of utilities, especially post-COVID, there have been supply chain issues and delays that have led to deferral of capacity expansion projects. When you combine all this together, you will see why the modern power grid is especially vulnerable to large-scale events such as natural disasters or cyber attacks. Now, while traditionally utilities have been focusing on the concept of resilience, during the past decade or so, they have also looked into resilience as a complementary factor. Reliability and resilience may at first be viewed in the same light, but they address two very different aspects of grid operation. Reliability focuses on common everyday life types of disturbances, but resilience deals with high impact, low probability events, events that are rare but could have catastrophic consequences. Despite the importance of resilience, we don't yet have a universally accepted definition for it. Most people refer to the definition by FERC, which says resilience is the ability to withstand and reduce the magnitude and duration of disruptive events, which includes the capability to anticipate, absorb, adapt to, and rapidly recover from that event. This is a more technical definition. The state of Colorado, on the other hand, defines resilience from the angle of communities. With that definition, resilience is the ability of communities to rebound, positively adapt to, or thrive amidst changing conditions or challenges, and to maintain quality of life, healthy growth, durable systems, economic vitality, and conservation of resources for present and future generations. With that definition, we consider both human-caused disasters as well as natural disasters. Now, regardless of the definition we pick, we should keep in mind that resilience should be modeled using the notion of risk. This is because of the rare nature of events that are considered in resilience studies. According to the expected utility theory, risk is defined as the probability of an event times its consequence, which means that probability of the event or its potentially catastrophic consequence should not be viewed in isolation, but in combination through the notion of risk. Now, to model resilience and be able to quantify the benefits of various mitigation strategies, the first thing we need to do is to define a metric related to system performance. This can really be anything. Can be energy not served, can be stability margin for voltage or frequency, can be voltage profile, system losses, or any other relevant metric, really. Once we define the metric, we assess its variations along the timeline of the event. Take a look at this diagram. Imagine I have defined a metric and I call it Q. Before the onset of the event, this metric has an initial value of Q of 0. When the event starts, it drops into a degraded state of Q of D, and it stays within that state for a certain period of time until recovery starts. Recovery is usually not a one-off action, so we oftentimes have a partial recovery and then full recovery to go back to pre-event conditions. Now, if we adopt resilience measures, we can improve certain aspects of this diagram. For example, we can reduce the level of degradation of that metric Q of T. Instead of going down to this level, we might go down to this level. We can shorten the duration of the degraded state before recovery starts, or we can speed up the recovery process. Now, speaking of resilience measures, these can be viewed based on the timeline of the strategy that we adopt. Typically, what we do is we look into measures that we can adopt before the onset of the event, during the course of the event, or after the event has run its course. These are known as preventive, corrective, and restorative measures. Preventive measures, think of it as infrastructural hardening, as introducing redundancy into grid design and operation, or preemptive event preventions. For example, public safety power shutoffs would be an example of that. Corrective measures, on the other hand, these are essentially risk-based energy dispatch strategies that utilities adopt under the various scenarios that they might lose certain assets or certain generation resources. One part of this would be to implement localized load shedding and load curtailment. And of course, once the event runs its course, we have to restore service to the outage area through a technique known as electric service restoration. Now, traditionally, these resilience measures have been implemented based on an engineering paradigm, which is generally a top-down view. We use engineering tools and methods to implement a solution to make the grid more resilient. In doing so, our focus is primarily on technical aspects of grid operation. When it comes to load, we often prioritize different load points based on economic metrics, the most common one being the value of lost load. And in addition, utilities often consider certain types of loads to be more critical and hence having higher priority for energization. Examples are hospitals, emergency rooms, fire stations, police stations, or municipal loads such as water treatment plants or wastewater management facilities. This view does not comprehensively model the impacts of power outages on society. So, in the recent years, a different view has emerged that tries to look at resilience based on the vulnerability or social vulnerability of individuals who are impacted by the event under study. Here, we try to take into account the impacts on the community by the large-scale and long-duration power outage. And we acknowledge the fact that not everyone feels and experiences long-duration power outages the same way. These outages could lead to health and safety issues or failure of essential services. Health and safety could be, for example, loss of heating and cooling, which could result in excess indoor temperatures, loss of food, loss of water services, or carbon monoxide poisoning due to inappropriate usage of diesel generators in indoor spaces. Failure of essential services could result in, for example, loss of access to medical facilities, to communication networks, transportation systems, or any other emergency response system. And the understanding is that different groups, different communities have various levels of adaptability and capacity when it comes to dealing with the consequences of these power outages. Now, a lot of research has been done focusing on social vulnerability against natural disasters. However, when it comes to studying vulnerability against long-duration power outages, this area is relatively unexplored. In an earlier work, we developed a multidimensional index of vulnerability against power outages based on 3 dimensions of health, preparedness, and evacuation. Health looks at being at risk of detrimental health effects during an outage. And a study of literature shows that there are various socioeconomic and demographic attributes that could result in higher vulnerability levels in that dimension. For example, age, being over the age of 65 or under the age of 5 can be a significant factor, or residents who rely on electricity dependent medical equipment, residents in nursing homes, residents with mobility limitations are generally shown in the literature to be more vulnerable. Preparedness looks into lacking access to clean water, food, medical supplies, and backup power. And again, a study of literature shows a variety of different attributes, socioeconomic and demographic, that could result in higher vulnerability levels in this particular dimension. And lastly, evacuation considers facing obstacles when being called to evacuate due to an outage. We consider individuals to be especially vulnerable in this dimension if they intend to evacuate but do not have the means to do so. And again, the review of the literature indicates various factors such as, the size of the household, households with children, people who have work constraints, the income level of the household, and a lot of other factors to have an impact on how vulnerable an individual or a household would be in this particular dimension. So using these three dimensions of vulnerability, we tried to develop an index for all the census tracts first for the state of Colorado and then for the entire United States. What we did was we referred to data from US Census, which is publicly available, and we also consulted some databases that were specific to individual states. We extracted that data, we cleaned it, we pre-processed it, and then we standardized and normalized it so that all these different variables have the same range of values so that they can be compared with one another. Then we applied principal component analysis to this very, very high dimensional data set to reduce the number of dimensions only by maintaining the variability in that data. And after applying PCA, we developed a vulnerability score based on the L2 norm or the Euclidean norm of the principal components. This gave us different numbers for different census tracts, and then we implemented a Pareto ranking in order to rank these census tracts from the most vulnerable to the least vulnerable, and then we mapped it into ArcGIS. The reference that I have provided here on this slide gives a lot more information about our approach if you're interested in learning more about it. Now, what we did was we implemented this analysis first for the state of Colorado. This shows you the different census tracts. Darker colors indicate higher vulnerabilities to power outages, and lighter colors indicate lower vulnerabilities. I want to point out that these geographical units that you see here, these are census tracts. A census tract is a geographical unit used by US Census and can house something between 1,000 to 8,000 residents. But the typical number across the country is 4,000, which is why you can see as we move away from high population areas in the state, the size of the census tracts become bigger because there's a larger geographical area where 4,000 people would live. If I zoom in to the city of Denver, again, you can see different census tracts within the city and where the more vulnerable and the less vulnerable communities and households are. Now, with this information at hand, we can perform power grid resilience in a socially aware fashion. This requires a hierarchical approach in which we consider both the spatiotemporal characteristic of the event under study, let's say a type of natural disaster, as well as the power grid, and then we overlay both of them on the map of the communities, on the map of social vulnerabilities of the communities, and assess everything within a unified framework. Let's take a look at the set of measures that we have for power grid resilience. In terms of preventive measures, when you're looking into infrastructure hardening or introducing redundancy into the grid, you can then prioritize areas, circuits, feeders in the grid that are more vulnerable, make them nominate them for being hardened or added additional resources. During the course of the event, especially when utilities want to implement load shedding and load curtailment, the priorities of these different nodes in different demand areas based on their social vulnerability level can be incorporated into the load shedding algorithm so that the load is cut from areas that need power less or are less vulnerable to loss of power. And naturally, for service restoration, the same logic applies. You restore circuits and feeders based on the level of social vulnerability of the individuals that are supplied by that feeder. To give you one example, this is a study that we did for the city of Greeley. I don't want to get into the details of the analysis that we did, just to show you that hierarchical model. On the left side, you see the map of the city of Greeley, the power distribution system with the different nodes, which is overlaid on the map of social vulnerabilities. So when you look at this map, the darker colors indicate higher vulnerabilities, hence indicating which nodes in this system would need to prioritize for infrastructure hardening, for any type of resilience measure that we have in mind. On the right side, we have the same distribution grid, which is now overlaid on the map of wildfire risk for the city of Greeley and the neighboring areas. Now we consider all this combined within a unified framework, We know where the risks are in terms of what circuits and feeders are likely to be impacted by the wildfire based on the probability. So that's the first component of risk. And then we also look at the consequence. So if a certain circuit is impacted and is out of service, what is the size of load that is going to be lost considering the social vulnerabilities of the customers that are connected to that node? So that would be the consequence aspect of the risk. So by looking at probability that comes from the wildfire map and consequence, which comes from the social vulnerability map, we can look into a risk-based analysis of this distribution system, in this case for the city of Greeley, in order to improve its resilience. In general, looking into power grid resilience from a social vulnerability aspect introduces challenges and opportunities. First of all, we would need to move away from a solely engineering-based paradigm towards one in which we are considering social vulnerabilities. This means that all the different types of events and disasters that we are considering must be modeled using the notion of risk. And social vulnerability of different load areas need to be modeled and quantified and be incorporated into any form of objective function that we are considering. This, however, introduces many challenges. First, risk-based models do not necessarily lead to any immediate return on investment. So they do require some form of a visionary approach. A utility might end up spending a significant amount of money for reinforcing a certain part of its circuit, which is supplying power to socially vulnerable populations. And they may not see the benefits of this for 5 to 10 years. But once a large scale event happens, the benefits of that strategy start to show. Another challenge here is that the social consequence of power outages cannot be easily quantified in financial terms. So, traditional concepts such as the value of lost load may not be easily incorporated into the notion of social vulnerability. One other challenge that we see in our work is that resilience and sustainability at times might have contradictory objectives, because with resilience, as a utility, you would try to introduce additional resources, more redundancy, stronger assets in order to achieve that certain level of performance. However, sustainability sometimes does the opposite. You want to do more with less resources. And these can at times be contradictory to one another, which is argued that both resilience and sustainability must be considered at the same time within a unified framework in any form of long-term design strategy. And another important aspect, which could be challenging, especially when it comes to implementing resilience measures that could have impacts on a community, is the voices and concerns of residents must be heard and must be incorporated into any form of strategy adopted by the power utility. This is often easier said than done because residents do not necessarily engage in a very efficient way with utilities. So, one good strategy might be to involve NGOs or community-based organizations in the policymaking to make sure all the different viewpoints, insights, pain points, every experience that these residents have are reflected in the strategies that are adopted for power grid resilience by the utility. This brings me to the end of this short presentation. Thank you for your attention. If you have any questions, if you would like to discuss any of these aspects, or if you would like to know more about the methodologies that we have developed, please feel free to email me. My contact information is here, and I would be happy to continue this offline. Thank you.